Okay, we'll make a start, Miguel. Now, apologies from Andrew Sturgis. He's unable to make it today. He would normally introduce Miguel, but as you probably all are aware, there's some severe fires going on in Queensland. So he's asked me to introduce Miguel on his behalf. So with no further ado, I will hand over to Miguel to talk about the investigations they've been doing into grass loads on grass fire behaviour. Thanks, Miguel.
Thanks, Deb. All right. Good afternoon, everyone. And so I'm talking here about some work we have been doing. We done last year, and it's linked to some work we have done in the past with CFA on grass fire behaviour. And just to give a bit of a background, when we were asked to do this work in specific of grass fuel load, this was a work contracted by Queensland Fire and Emergency Services, and it was to look at the effect of high grass fuel loads on grass fire behaviour. So just bear in mind that's looking at the effect of fuel load on the high end of the spectrum of fuel load, right? Before I started, I just want to also acknowledge the people that enable this work to go forward, not just by providing some of the funding for the project itself, but more importantly, to allow us to find, or for them to find the suitable sites, making sure we had firefighting resources available when you're doing the burns, and most importantly, allow us to burn in conditions that we wanted, namely in quite high fire potential days. Namely, we burned a few fires in GFDIs higher than 50 and in days of total fire bans. So without support of some of these names, Andrew Sturgis, Simon Imstra, Lawrence McCoy, Rachel Bassel, and Alan Slipovich, without their support, we will not be able to get the data that we got to do the analysis that we end up doing. So that from these guys needs to be mentioned. Now, while you're fresh on the presentation, let me just make a note on the goodness of fit of fire models. This raised after previous presentation where I got some questions after when I talked about bias and goodness of fit of models. And this will come later in this presentation, and I just want to clarify this to you. So we have two models, one in the red on the left, and one on green on the right. So what you see, if you look at the red dots, you see model predictions of observed rates of spread. And we have those graphs, the scatter plot, we have a line of perfect agreement. That's where we want to have the data points on. Each of these data points is a wildfire observation and a prediction for that observation given the weather conditions and the fuel characteristics. So the model on the left, you will see that all the data points, of most of them, are to the left of that line of perfect agreement, and there's an under-prediction bias. So the model predictions are much lower than the observed rates of spread. As a trend, this model, as that line says there, has a slope of 1.7, meaning that you need to multiply the prediction by 1.7 to get the right result, right? And so that's not a case where we have a biased model with an under-prediction bias. On the right-hand side, we have that those green points and a different model, and we get that trend line saying that you need to only multiply the results by 1.04 to get accurate results. So this will be a model that basically has no bias. There's a lot of scatter in that data, and that scatter comes from the fact that it's data from wildfires, that a lot of uncertainty into the fire behavior measurements and the wind and the fuel moisture and rates of the fuel condition. So all that uncertainty makes that there's a bit of spread around that line of personal agreement. But that's okay. What's important is that the results are not biased, right? The trend is a faithful representation of what we want to achieve. So in this graph here, I just put those data points together and I put some statistics for those two models. That MAE you see is the mean absolute error. For the red model and for the green, you see there's a reduction, but it's not too much, right? From 14 to 9, right? But the main difference you see is when this MBE, the mean bias error, the value that quantifies this bias, goes from 12, minus 12, essentially very close to the mean error, to minus 1.5, so very reduced bias, right? So this is just a quick note. That's what we want with the models. When you develop models with no bias or very reduced bias, right? That's why I like this point. And now I go to the presentation itself. So, why do we want to know the grass fuel effect on grass fire behavior? Some of you might even ask, don't we know that already? And it's a bit of convoluted aspect in terms of fire research and application of fire research in management. Initially, when Alan MacArthur first developed the grassland fire danger meter, he had a direct effect of fuel load on fire spread, same as we have in the forest fire danger meter. So we double fuel load, that would mean that you double the rate of spread. Now, later, Alan MacArthur came to the conclusion that maybe that effect should not be present. And the reason he gave for that was that normally low fuel load grasslands are made of fine grasses. And high fuel load grasslands structurally are made of coarse grasses. So we have here fuel coarse or fuel thickness, a surface volume to ratio or surface area to volume ratio effect. That would cancel because you know fine fuels burn quicker than coarse fuels, and so if there was an effect of fuel load, this fuel size effect would cancel that fuel load effect. So we decided to remove the effect of fuel load from the meter. Now sometime later, somebody brought back the effect, namely for GFDI calculation, and that in particular creates some problems in Northern Australia, where GFDI being calculated with a grass fuel effect tends to give results of fire potential, fire danger rating much higher than what was being observed. So that's why and researchers come back to us and ask, can you look into that? Can you look into this effect again and see if this effect exists or not? Because we're getting too much restrictions, given the high fuel loads we get up here, up north, and some of the invasive species like gamba grass, and we are not observing that kind of fire behavior. So that's how this project came about. Now, another important point before I go into detail in here is that there's some practical issues when you introduce fuel load effect to calculate spread rates of grasslands, right? The three models that exist for grassland fire spread are based on a fuel condition: natural and undisturbed grasses, grazed grasses, and eaten out grasses. And so there are three equations, one of each for each condition. Now, some people have been using fuel load as a surrogate of fuel condition, right? And you can see in this graph on the right that these values here, these coarse lines, are the average values for studies that we found. And you have ungrazed, grazed, and eaten out. And there's definitely effect of or decrease in fuel load from the ungrazed to the grazed and to the eaten out. Right? But although there's this general effect, there's also some overlap. So if you go from the ungrazed and assume a certain fuel load to the grazed with a different fuel load, we see that there's a lot of ungrazed conditions that fit into the grazed envelope, right? So you can go one way, but you cannot go the other way, right? And as curiosity, this graph also shows here the suggested range of fuel load that Alan McCartan came up with, 5 to 10 or 4 to 5 tons per hectare. I'm sorry, these graphs are in kilograms per square meter. You just multiply by 10 to get the tons per hectare. But this is the value that McCartan suggested. And all the sampling, or most of the sampling we've been finding in Australia is much lower, not only in southern Australia, much lower than these 4 to 5 tons. There's some exotics, much higher values, but as a trend, we have lower values. Another point is if you use fuel load to meet rate of spread expectations, meaning you have a load driving the fire spread model, and you modify the fuel load, namely increase the fuel load to get the right rate of spread, your fire line intensity might be off by a factor 2 or 3. So, going through this fuel load on rate of spread has been present for many, many years in Australia. And back in the 80s, there was a large experimental burning program in Northern Australia that specifically aimed to look at this effect. And this is a study that Phil Cheney and Jim Gould conducted, the Annaburu experiments, that are the base of the rate of the grassland fire rate of spread model that we use in Australia. An issue that exists with this data set is that the range was mostly from 3 to 5 tons, right? Which doesn't cover some of the high fuel loads that we have been observing in tropical Australia. Now, what happens when it's 10 tons per hectare, right? That's what was the question we were asked to look at. When Phil and Jim conducted study for this range of fuel loads, 3 to 5 tons per hectare, they found no effect of fuel load on rate of fire spread. So, no effect, but with this caveat, between 3 to 5 tons per hectare. So, to look into the effect for much higher fuel loads that Queensland Fire Service assessed, our approach was, okay, let's do some fires, let's do some burns, and see what we observe. So the idea is like, okay, let's set some experimental fires, and they're really, or under higher fuel loads than the previous burns. I mentioned here between 7 and 12 tons per hectare. And if you do these burns in large plots, 200 by 200 meters, we would be able then to compare our results from these burns with the existing models. And if we'll find that the existing model would over-predict, or let's say the under-predict rate of spread, would mean that these fires would be, that we conducted, was spreading much faster than the model was saying that high fuel loads will result in higher spread rates. If it was the opposite, the results would say that high fuel loads would result in lower spread rates. So we found the site. There's a photo of the site we found in Northern Territory. Unfortunately, the site just kept burning. He burned twice over 2 burn seasons, and so after 1 year and a half, we had already put quite considerable effort on the project, but we were not able to get any data. And so we came up with a backup plan. And what we thought, within this work we have conducted with CSA and also RFS in New South Wales on the effect of gas curing in rates of spread. We had conducted more than 100 burns, but about 50 burns were in fully cured grasslands. And here we have the map of Australia with the spread of these sites in New South Wales and Victoria, and also one site in Queensland when he did these burns in plots. They were 33 by 33 meters, and where we burn under controlled conditions or non-conditions to quantify the effect of grass curing. So the backup plan was, okay, let's try to find a site with high fuel loads, much higher than what we had up to now, and conduct the same type of burns. And then we join all the data sets together, and you do an analysis and see what the analysis gives us. Now, I might ask Deb to play one of the videos. Yeah, it could be this Amberley first video. So now just to illustrate the burns we conducted. Okay, we needed to go to the beginning. Thanks, Deb. So again, this is a high fuel load condition. You see the grass is quite broken because as they are tall and coarse, they try to broken more with time. A 33 by 33 plot. This is about 9 to 10 tons per hectare. Fuel load, we light a fire, a line fire, and let it go. You can see here heavy fuels, quite a deep flaming front. That's all good. That's an example of one of our fires. I'll ask them to put the other video. Yeah, Braidwood. So this is a good example of a very light fuel load. This is about 2 tons per hectare, so 5 times lower than the previous one. There are some issues here with the ignition, not a problem. We only measure rates of spread in the second half of the plot after the flame front got its parabolic shape. That's really characteristic of a wildfire. And that's a burn, another example of another burn. So this was very light fuel. You see here easily on the second video, the flaming front much and not as deep as this one. Fires, although it's difficult to say, there's always variation in wind and fuel moisture, but these spread faster, right? Okay, I might go back to the presentation. So, after we conduct these burns in Queensland, in the end we have about 58 experimental fires that we could use for the analysis. Wind speed varies between 5 and 37 kilometers per hour. Fuel loads from about 2 tons to about 11 tons per hectare. Depth fuel moisture is between 2.5 to about 13%. Rates of spread up to 150 meters per minute, and fire intensity up to almost 19,000 kilowatts per meter. So that's what we had available for our analysis. Here, just to show the differences between the fuel loads, distributions for different sites. So for the grass curing burns, that's these Bell, Ballarat, Braidwood, Tamworth, Toowoomba, and Wangaratta. That's fuel loads we're getting in these more southern grasslands, besides the Tamworth, that's also like or subtropical. And for Amberley, we get values up here. So whereas for the first section, we have from 1.7 to 6 tons. For the burns in Amberley in Queensland, so that's the heavy fuel loads, we have from about 7 to 12 tons per hectare, right? And that results in this bimodal distribution of fuel load you see in this graph. Okay, so what happens when we put all our data together? Because there's a lot of variables, variable wind, fuel moisture. It's a bit difficult to put everything in one graph. This graph really tries to bring all together where I have rate of spread as a function of GFDI, right? The original GFDI without fuel load effect. And the dots, the size of the blobs are related to the fuel loads, right? And you use GFDI here because you homogenize the effect of wind speed and fuel moisture content, right? So it brings everything to the same ruler, and then we have GFDI rate of spread. What we can see in this graph is that the high fuel loads, like the big blobs, are all in the bottom of the graph. And the small blobs that are relative to low fuel loads are kind of higher in the graph. So for the same GFDI, we are getting fires in the fine fuels and fine low fuels spreading faster than the fires in the high fuel loads, right? That's very interesting in itself because it's opposite to what the original effect was thought to be. And let's also make a point here that the original effect was not based on any fire data in grasslands, was an extrapolation of the effect found for forests, namely for prescribed burns in forests, to grasslands. Right? So the next thing we wanted to do is like, okay, let's quantify this effect, right? And for this, you use some statistics. In this case, we use multiple linear regression analysis, where we're going to regress the effect of wind speed, moisture content, and fuel load, is W here, on rate of spread. So we did through this linear regression analysis, the analysis takes into account all these possible combinations and spits out an effect. Here we have the spread of the residuals, so kind of homogeneous, and on the left side we have the effect of fuel load. So as the fuel load increases, rate of spread decreases. Right. What we got in here is a study from Phil Cheney and Jim Gould in Annaburu, is that in our analysis, because we have a higher spread on fuel load, we found that fuel load was a significant predictor of rate of spread. So significant predictor is just that higher fuel loads result in slower rate of spread. Now, whatever comes from this regression analysis cannot be implemented directly in the models that we use, in the Bushfire spread models that you use, because the coefficients are inherent to this regression analysis, to this database. So the next step in our study was to try to come with a way that we'll be able to implement the effect we found in the grass fire spread model, right? So first what we did is to run linear graph-fire spread model against our data set. Right? We have measured wind speeds, or measured fuel moistures, or measured curing, and you compare the model outputs with our observations. And this is the plot. So we have a mean average absolute error of about 19. Not much of a bias, 1.3. So this is about 6% of the mean error. So really small bias. And at the mean, the error as a percent was about 31%. And this is as low as normally when you do these empirical studies of fire behavior, this is as low as the errors get, 30%, 35%. So that's very encouraging, and that's what we kind of expected in terms of the error side. But what we're surprised with was the bias, no bias. And why we were surprised was because this model is based on wildfire data sets and some experimental fires, so large fire fronts. And our data set is based on small fires, 33 by 33 meter fires. So you'd expect to have a certain effect there. You'd expect that the model would predict higher rates of spread than our data is because of that size effect. But we didn't find an effect because there's no bias in this. So that's interesting. It might have to do with our ignition being different from what original ignition done in the Enebu studies. But also this allows us to continue this analysis using the current model. So, although no bias, no general bias, very small, what happened when you look at the residuals of these predictions, we see that the data in the very high fuel loads tend to be over-predicted, right? So again, because of the fires in high fuel loads seem to be spreading slower than in the low fuel loads, we are getting the model to over-predict these fires. And here are the errors for this particular high fuel load data set, where there's the bias went from 1.3 meters per meter here to about 16, so almost 10 times larger, and mean absolute percent error went from 31 to 5. So what we want to do now is you need to find a way that we reduce this bias. So we are happy with the model performance in this lower range. So can we change the model? Can you add something to the model that will allow the model to continue to predict correctly in this range, but improve the prediction in this range, right? So that was the next part of the work. So this is the form of this rate spread model, that the grassland fire rate of spread model, where you have rate of spread as a function of a wind function, a depth fuel moisture function, and a curing level function. They all multiplied. And then the idea was, can we add a fuel load effect to the model? But important here is that whatever we add maintains the model integrity, meaning it doesn't change the model outputs for those more normal Southern Australia fuel loads between, let's say, 3 and 5 or 6 tons per hectare. That's going to allow to improve the prediction of the model to our data set for those very high fuel loads. So we tried different forms, could you add different functions, let's say, and you found this function that this graph shows the general shape, where it starts for a low value, it ends like a bit of a plateau, and then slowly decrease These are called a recur function. And so let's say we have low values for very low, very sparse fuel loads. Then for that average Southern Australia fuel loads between 3 and 5 tons per hectare, we have this plateau. And then for the very high fuel loads, there's a slight decrease or continuous decrease in fuel loads. So that's the function we wanted to apply, or the one we found to be most adequate. And we just need to find the parameters, these parameters that will make the data set, the model fit our data set effectively. And after we did this, so we did this analysis, we found these parameters, and this is what we came up with. This again is the residuals. Not much change in the lower hand, although there's a bit of a tightening of the residuals, what was good. But in high hand, where we're looking into, we reduced the mean absolute error from 20 to 13, highest from 16 to 6, and this made the mean absolute percent error from 55 to 36. This is the error as a percentage of the observation. That's what we got in the end with this new function. So we're pretty happy with it. So this is the old original model residuals, and you can see how we're able to squeeze all those residuals and move more residuals and a more balanced distribution. Another thing we did in this study is to look into the effect of load on flame height. Again, existing flame height model is based on just fuel condition, natural pasture or grass, and the model only considers the effect of rate of spread. Right? This is the graph that comes from the Bushfire's book. So when we conduct our fires, and after analyzing our fires, we again go back to the early graph I showed in this similar, but with flame height in the y-axis. What we see is that for any given GFPI, the high fuel loads, big blobs, are much higher than the little blobs, right? So just say, okay, high fuel loads is decreasing rate of spread, but is increasing flame height. And that effect of fuel load on flame height is not present in the models for flame height that we are currently using. So we did similarly, we did some regression analysis, and we estimate flame height as a function of rate of spread and fuel load. In our analysis, fuel load was found a significant predictor of flame height. Here is just a graph of observed flame heights and predicted flame heights. So in this case, there's no independent data, so everything fits nicely because the data was used to develop the regression. Right? And here in this graph on the right, we have the previous model, this dashed line, with a predicted flame height as a function of rate of spread. But in this case, we have curves for 2 tons, 4 tons, 8 tons, and 12 tons per hectare. And you see the effect in the new model of this fuel load on the flame height that was not present in the model. So also pretty happy with these kind of results, kind of improving for flame height. So just as presentation kind of going long, some concluding remarks, like take-home messages. Fuel load was found to be negatively correlated with rate of fire spread in grassland. Right? So that was contrary to the previous wisdom. Now, a bit of a caveat. This effect is not constant with fuel load, right? There's pretty much negligible effect between 1.5 and 4.5 tons per hectare. So within that range, not much of effect. It's really when you go for more than 6 tons per hectare that we are seeing that progressive decay. So, yes, overall, there's this negative effect, but it's not constant. And so that's where also we point here. We develop a fuel load effect function that can be implemented in CSIRO's rate of fire spread model. This is only for the ungrade, for natural conditions, but this function is not only necessary for very high fuel loads, grasslands. So if you are working in the normal range, 3-5 tons per hectare, you really don't need to worry about this effect for rate of fire spread. You might be wanting to use that for the effect on flame height, if that is applied. Further questions we have here. What happens when fuel load is lower than 1.5 tons per hectare? We don't know. We didn't look into that because we don't have data to tell us that. Namely, when grasslands start to become quite sparse and the fuel load is marginal, what's happening there, we don't know. We didn't address that. Also to note that what we found here for fuel loads in terms of fuel load effect, is very similar to what Neil Barrows found for spinifex grasslands. He also found that increasing fuel load results in a decrease in rates of fire spread. Although he was not able to find a significant effect. He found the effect, but was just not statistically significant. But the effect was there. So with this, finish my presentation, and I'll be more than happy to answer some questions, some doubts you have about the study. Thank you.
Thanks very much, Miguel. Does anybody have any questions for Miguel? Sounds like you covered off on it quite well then, Miguel.
No way.
Okay then. Well, thanks again, Miguel, for your presentation today, and thank you everyone for attending.